Okay, welcome to AP Physics C Prep Day 1, Part 2. Topic of this is what is calculus? Let's get started. By the end of this lesson, you should understand the requirements, materials, goals, and procedures for this course, the inputs and outputs of derivatives, indefinite integrals, and definite integrals, how to take a limit using a combination of algebraic manipulations and substitution, and how to take a derivative by graphing and drawing tangent lines. Now, just as a side note, usually the learning objectives will be listed early, listed as the first slide of Part 1 of any lesson, but for this particular lesson, this particular day, we had to cover the broader course overview topics, and learning objectives don't make a whole lot of sense unless you understand the overall objectives and mechanics of the course. As I implied in the last slide, there are three basic operations of calculus. The first one we're going to talk about is the derivative. Now, a derivative is an operation which converts a function into the rate at which that function changes. So anytime you hear the word rate, it means a derivative. Just to clarify or repeat myself, the input for a derivative is a function, and the output of a derivative is the rate of change. So for example, velocity, which is really similar to speed, the only difference between velocity and speed is that velocity has some direction, so it can be negative, it can be two-dimensional, etc. But let's just keep things simple. For now, you can assume that velocity and speed are the same thing. Velocity is the rate of change in position. You can rephrase this to say the derivative of position is velocity. Notice that the word velocity switched, the words velocity and position switched their order in this second statement, but the two statements absolutely mean the same thing. A third way to restate this is to say that velocity is the derivative of position. And again, once again, the position and velocity switch locations in the sentence. All three of these sentences mean the same thing. The second of the three basic operations of calculus is called an indefinite integral, or it's also called an antiderivative. Now, if you're watching this and you're a good calculus student, you'll know that there are slight differences between an indefinite integral and an antiderivative. For the purposes of this class, it's going to be all the same, and remember, this is just a limited calculus course, just enough to get you through AP Physics C. So if a derivative had an input as a function and an output as the rate of change, an indefinite integral does the opposite. An indefinite integral is an operation which converts the rate of change back into the original function. You can think of it as the inverse operation of a derivative. The indefinite integral and the derivative operations will cancel each other out if they are performed sequentially, and it doesn't matter in what sequence. You can do the indefinite integral first and the derivative, you can do the derivative first, and then you can do the indefinite integral. They cancel each other out just the same way multiplying by 5 and dividing by 5. Those two operations will cancel each other out as well. Okay, so to represent this visually, if you have a function and you take the derivative of that function, then you get the rate of change. So for the operation that we call a derivative, the input is a function, and the output is the rate of change in that function. Indefinite integrals, otherwise known as antiderivatives, are the exact reverse of this process. The input for an indefinite integral or antiderivative is the rate of change, and the output is a function, or is the original function. Now, here's something that's a little weird. The rate of change in a function can or is also a function. Now, this gets a little clearer once you hear a definite an example of this. So let's go back to position and velocity. Our function would be position. Rate of change in that function is velocity. Now, position is not just a singular quantity. It's a whole collection of quantities. In fact, your position can change as time changes. If we all just stayed still, this would be a pretty boring world. So your position changes as a function of time. And if you take the derivative of position with respect to time, you get the rate of change in position with respect to time, otherwise known as velocity. Now, your velocity also does not have to be a singular number. If you just look at the speedometer on your car, your speedometer basically tells you what your velocity is, and the fact that it's a whole dial means that that number can change. So your rate of change can change. And since it changes as a function of time, that makes it a function. The other way to think about this is to go back to the definition of a function, that you probably learned back in algebra, which is a function is any set of collection of points which passes the vertical line test. Your original function will pass the vertical line test, so can the rate of change of that function. Okay, so the last of the three basic operations of calculus is called a definite integral. And it's usually described as the area under a curve. But more specifically, it's the area under a curve and between two boundaries, and pretty much every calculus book that I've ever seen calls those boundaries the lower boundary A, that's the boundary that you start at, and the upper boundary is called B. So your definite integral is defined as under the curve and between A and B. Now, another interesting twist on the definite integral is that your areas can be negative. So, which areas are negative? The areas below the x-axis are negative, and also definite integrals have some direction to them, right? I said you started at A and you end at B, so you go from A to B, and that means they've got some direction to them. So definite integrals taken from left to right are positive, and definite integrals taken from right to left are negative. Now, if you put all of these rules together, the easiest way to summarize it is in a chart like this. On this axis of the chart, you have the direction of the integral, left to right. And on this axis of the chart, you have whether the curve is above the horizontal axis, that is the x-axis, or below the x-axis. And for every combination, you get either positive or negative areas. So if you are integrating from left to right and your curve is above the horizontal axis, that will give you a positive area. If you're integrating from right to left and your area is still above the horizontal axis, you will have a negative area. If your area is below the horizontal axis and you're integrating from left to right, then your area is negative. And if you're integrating from right to left and your curve is below the horizontal axis, then that will give you a positive area. I'll show you what this means in two examples, or really two variations on one example. Okay, so let's take a look at an example. Let's say we've got this function. The axes are in black. The function is in gold. And this kind of looks like a sine function, but it's a little too straight in the middle. It's just something I knocked together using the PowerPoint graphic tools. Okay, so as I said in the previous slide, in order to take a definite integral, you need a function and you need two boundaries. So we got our function here, And there's our lower boundary, A. It's at the origin. And here's our upper boundary, B. It'll be right there. And since we're integrating from A to B, that means our direction of integration is from left to right. And since we're integrating from left to right, that means the area above the curve is positive. And similarly, the area below the curve is negative. Now, you might have noticed that this area is about the same as this area. There's about as much space in this blue spot here as there is in this red spot here. So both areas are about the same. We have about as much positive area as we have negative area. And that means when we add the total area together, we're going to get a definite integral that is nearly 0. This is like saying plus 5 and minus 5, plus 5 plus minus 5, or positive 5 plus negative 5 is 0. Now, I say the areas are about the same and the definite integral is nearly 0 because we're just kind of eyeballing this, and without some formulas and numbers, we can't tell for sure, but looks about the same. So you would expect an answer that is nearly 0, and if you got an answer that's drastically different from 0, you probably did something wrong. Let's look at this same function, except we're going to swap the boundaries around. We're going to put A right here, and we're going to put our upper boundary B at the origin. And again, we're still integrating from A to B. So our direction of integration this time is from right to left. And that changes everything around. When you're integrating from right to left, the area below the curve is positive, and the area above the curve is negative. But we're still looking at about the same amount of space here as we are here. So both areas are still about the same absolute value, or it's about the same amount of space. It's just one of them's positive and one of them's negative. And that means that the definite integral will again be nearly 0. All right, so to just reiterate the basic inputs and outputs of a definite integral, for a definite integral, you have to start out with a function and its boundaries. If you perform the operation of a definite integral on a function and its boundaries, you get the area under the function, or slightly more accurate to say that it's the area between the function and the horizontal axis. Now, area is a number. It is not a function, it's just one single number. If you were to calculate the area of, say, a 5 centimeter by 6 centimeters square, you would get 30 square centimeters. Similarly, the outputs of definite integrals are single individual numbers, not some function of x or y or t or whatever. Okay? It's just a number. And that's where you get the term definite integral. You get much more definite answers than you would from an indefinite integral. Okay, let's do some practice on this. And I'll pull an example from economics. The cost of an item C is a function of the quantity made Q. The marginal cost M is defined as the rate of change in cost C as the quantity of items is increased. Which statement is true about M of Q and C of Q? Both M and C are functions of Q. Now, just as a side note, this reflects the fact that the more you make of something, usually the cheaper it is to make each item. So you have 4 possible answers. M is the derivative of C. C is the derivative of M. M is the indefinite integral of C. C is the definite integral of M. Pause the video a bit, read this over, and see if you can figure out the answer. Okay, hopefully you've paused the video and checked out the answer. The key thing to read into this is the rate of change in cost. Marginal cost is defined as the rate of change in cost, and that means that M is the derivative of C. And so the correct answer is A. M is the derivative of C. Okay, let's take a slightly more complicated problem. In material science, a common experiment is a tensile test. In this test, a sample of material is pulled apart until it breaks. Based on data collected during this experiment, the stress, abbreviated with the Greek letter sigma, and the strain, abbreviated with the Greek letter epsilon, are calculated. Don't get freaked out by the Greek letters. They're just other ways of writing the same thing, like X and Y or F and H and G and all of those, okay? They're just more variables, more abbreviations. So stress and strain are calculated, and stress is plotted as a function of strain. So you get a graph with these axes, and it'll typically look like this, especially for a metal. The area under this curve is called toughness. So toughness is going to be that blue zone that just got filled in. Materials with low toughness are brittle. So, for example, glass is brittle, or at least brittle in the common everyday person's definition. Those of you who are in material science have a slightly different definition of brittle, but for those of us outside the field, low toughness means brittle. Which of the following statements are true? Stress is the derivative of strain. Toughness is the indefinite integral of stress. I completely read statement 1 incorrectly, so let me try this again. Toughness is the definite integral of stress. Toughness is positive for this graph. Now, another thing I'd like to note is that this three-statement system, this is how the AP exam does true-false. Okay? When you see these three-statement systems, think of this as just three separate true-false questions, and then over here you get a bunch of answers as to which combination of true-falses are correct. Okay, pause the video, take a look at each of these three statements. One of them may be true, some of them may be true, all of them may be true. You got to figure out the right combination, and then select the answer A, B, C, D, or E, which matches your particular combination. Okay, so you've paused the video, you've checked this out. All right, let's take these statements one at a time. Stress is the derivative of strain. Okay, in order to have a derivative, you have to have the rate of change in here somewhere, and nowhere in all of these words does the term derivative or rate of change show up. Okay, stress is a function of strain, but it is not a derivative of strain. So, statement 1 is false, and that automatically rules out answer A, C, and E. So at this point, if you had to guess, it would be either B or D. But let's not guess. Let's actually work this out. Statement number 2, toughness is the definite integral of stress. Okay, so I said the area under this curve is called toughness. And we also said that stress is our function. So we're taking the area under a function, the area under a curve. So this statement is true. Toughness is the area under the curve, and area under the curves are definite integrals. So therefore, toughness is the definite integral of stress. Last statement, toughness is positive for this graph. Well, the fact that I did it in blue should have been a hint. When you start these tests, you obviously start by not pulling on it, and then you pull on it more and more and more and more and more, and so there is some directionality to this graph. It starts at the origin and then proceeds this way, and so if we're going to take the integral, it's going to be in this direction. In other words, it's going to go from left to right. And that means, and this curve is above the horizontal axis. The gold curve is above the horizontal axis. So integrating from left to right, curve above the horizontal axis, that means that this area here, this blue area, is positive. So statement 3 is true, and therefore both statements 2 and 3 are true, and therefore the correct answer is D. Okay, so this problem is a bit more complicated, and if you don't get this one, don't be too surprised. Okay, so or don't feel too bad. Many systems undergo a cycle in which a system is charged and then discharged. When it discharges, not all the energy comes back in the same form as when it was charged. So think of recharging a battery and then discharging that same battery. You have to put in a little bit more energy than you get out. If you have a highly efficient battery, if you have a really inefficient battery, you got to put in a lot of energy, and then you don't get out a whole lot of energy, or at least not a whole lot of electrical energy. What happens is some of that electrical energy gets converted into heat. Okay, so you can do this you can think of charge-discharge cycles on electrical systems like batteries or capacitors. You can think of charge-discharge cycles on mechanical systems like a rubber band. You can charge a rubber band by pulling it apart, and the rubber band will store the energy that you put in, and then you can discharge the rubber band by letting it go, and that stored energy will be discharged in the form of a mechanical contraction. Okay, so a lot of systems undergo this charge-discharge cycle, and for anything that undergoes a charge-discharge cycle, you can have something called hysteresis. Hysteresis is defined as the area between the charging curve and the discharging curve. Restate the definition of hysteresis using calculus operations. Okay, in general, something that you should do for any complicated problem, whether that's, well, especially in physics, but in life in general, a way of processing information in complicated problems is to draw some sort of diagram. So if we have a pair of axes like this, and we charge something up by putting energy in, and we track the amount of energy that we put in, we'll get a charging curve like this. Maybe it'll look like this, maybe it'll be something a little different. And then we discharge that system, it'll give us a discharge curve that looks something like this. And it says, the problem states, hysteresis is defined as the area between the charging curve and the discharging curve. So what we want for hysteresis is this gray area here. Okay, so restate a definition for the gray area using calculus operations. So give me a definition. This gray area is the same thing as hysteresis. Pause the video now, think it over. Alright, if you thought it over and got to an answer, cool. If you need a bit of a hint, here's your hint. Alright, so you can think of this gray area as a combination of two things. So the gray area is equal to some combination of the area under the outgoing curve and the area under the returning curve, or the area under the charging curve and the area under the discharging curve. And the fact that I've drawn these in blue and red again should again be a hint. Alright, pause the video again if you are going to use that hint to finish solving the problem. Okay, so area under the charging curve, according to our definitions of positive and negative areas, is going to be positive. Area under the discharging curve, according to our definitions of positive and negative, are going to be negative, and that's because the discharging is from the charged state back to the origin, and so that is a integration from right to left. And the fact that we're taking area under the curve in both cases means that these curves are synonymous, are the same thing as definite integrals. And we want to add these together in order to take this stuff without the overlap from this in order to get that. So, hysteresis is going to equal the definite integral of the charging curve plus the definite integral of the discharging curve. Now, you might be thinking that shouldn't this positive sign be a negative? Well, in some way we want to take this area, the red area, away from the positive, away from the blue area. But the fact that this is already going to be a negative definite integral means that this will already be negative, and so we add them in order to take this stuff away from this stuff. A positive plus a negative is the same thing as a subtraction problem. Okay, so up next is going to be another video on the sort of general introduction to specifically to derivatives, and that's going to be I'm going to just hand it over to Sal Khan and allow him to explain it. This video will start automatically if you are using the AP Physics C Prep Day 1 playlist, and if you are not, then you can type this URL into your browser and get the next video. Although I strongly suggest that you use the playlist, that way you get all the parts that come after the Khan Academy video.